Welcome back, everyone. Now that we've learned about the different parts of chemical equations and how to balance them, it is time for us to start learning about the types of chemical reactions. Here in part 3 of the Chapter 6 outline, we will learn about the 5 fundamental types of reactions. We will learn these 5 types of reactions over the course of several lessons. Here in this first lesson, we will learn about the first 3 types: combination reactions, decomposition reactions, and combustion reactions. In subsequent lessons, we will learn about the different types of displacement reactions, that is, single and double displacement reactions. As we go through these various sections learning about different types of chemical reactions, keep some of these points in mind. They're kind of like goals that you should strive for as you're learning about these different chemical reactions. So for example, hopefully you should be able to look at different reactions that we see later on after you've learned about them and classify that type of reaction. Also, of course, you should be able to balance the various types of reactions. Some types, as you will see, have their own unique style and little tricks that we use when we're balancing them. You should also be able to identify the phases of various substances. So I'll show you some tips down below, but for example, you'll note that most metals are solids, and we're going to assume that ionic compounds are solids as well, and you'll learn about the different types of gases and liquids and that sort of thing. So that's another thing that you should be learning as we go through all of this. Finally, as you're learning about these different types of chemical reactions, what I really want you to learn how to do is start to predict the products of these different categories. So as we're learning about combustion or single and double displacement reactions, looking at the reactants and then being able to write down what you would predict are the products is definitely a key skill that you want to pick up from this. Here in the notes, I've written down a few points that will help us as we're starting out writing chemical equations for the various reactions we learn. So for example, let's try to remember that all metals are solids. Now, this is true with the exception, of course, of mercury, which I have listed down here in the liquid section. Also, the other liquids that are elements are bromine, and then we have also water, of course, is a liquid, though that's a compound, not an element. We're also going to assume, for the purposes of this class, that all ionic compounds are solids. So when we see a metal with a nonmetal, we're just going to assume that it's a solid. That's actually most likely true because most ionic compounds are solids in their normal state. There are some examples that are a little bit more exotic of ionic liquids, but we're not going to be talking about those. And then finally, gases. That's probably the most difficult one, or the one that you are unaware of, I guess, at this point. So let's write down what are the common gases. So we have a lot of elements that are gases. Those are mostly nonmetal diatomic elements. So let's summarize those. We have as gases hydrogen gas, nitrogen gas, oxygen gas, and then all of the halogens are also gases. So that's fluorine, chlorine, bromine, and iodine. Those are the gaseous elements. And of course, the noble gases as well. But as you've learned, noble gases don't react with anything, so we're not going to see those involved in chemical reactions for the most part. Now, there are some other common gases that I want to summarize for you, but we're going to hold off on that for now because it's better in probably a different part of the lesson. So for now, I want you to keep in mind the elements that are gases. That's going to really help us. So we'll come back to these other gases later. Now, let's go ahead and get started learning about chemical reactions, and we're going to start with the first one on our list, which is the combination reaction. So let's learn what is a combination reaction, how does it work, and then we're going to do some examples of it and write some equations. So let's go ahead and get started. So what is a combination reaction? Well, as you might expect from the name, a combination reaction involves taking multiple substances and combining them. Most commonly, when we see a combination reaction, it involves combining two things into one thing. So we have two substances that combine to form one substance. We can write this down in generic symbolic terms using symbols like A, B, and C. So in a combination reaction, it would look like A combining with B, where A and B are different substances, into some new substance that we'll call C. These are often referred to as synthesis reactions because we're putting something new together. Notice that we use the plus sign over here to represent the fact that we need to actually have A and B, the two different substances that are combining, in the same place at the same time. So we're using the plus sign here like the word and. So we're taking A and B. The actual reaction itself, in this case, the combination reaction, is the change that's occurring, and that's actually symbolized by the arrow that we have going forward. So now let's take a look at an actual combination reaction. Here in this first example, I have the word equation describing a combination between magnesium metal and chlorine gas. Let's read through it, and then what we're going to do is translate this into a chemical equation and then go through the process of balancing it. So it reads like this. Magnesium metal is combined with chlorine gas to form magnesium chloride. Okay, so we have this sentence describing a chemical reaction, and what we want to do now is translate this sentence into a chemical equation that describes what's going on. In order to do that, we need to make sure we have all of the right symbols in all of the right ratios and combinations with subscripts, coefficients, phases, all that kind of stuff. So how do we go about doing that? So I'm going to show you how, and the way I like to teach this is by showing you a 4-step method that we follow whenever we have to do this kind of thing. Now, it's really important that we actually do these 4 steps in this order. One of the more common things for people to have an issue with is forgetting one of these steps or doing them out of order. And when you do that, what ends up happening is it becomes sort of difficult or sometimes impossible to actually get it right because of the mixed up of the orders that you're doing it in. So I'm going to show you each of these 4 steps with this example and the rest as we go through it. I apologize if it's a little repetitive, us looking at these 4 steps each time, but I really want to make sure that I get this kind of into your head and sort of brainwash you to use these 4 steps each time. So let's go through the 4 steps with this example. Before we jump into this example though, make sure you've written these 4 steps down. So if you need to pause the video for a second and get maybe a separate piece of paper or your lecture note outline, wherever you want to write it, and jot these down. So let's go ahead and get started looking at these 4 steps with this first example. So as you can see, the first step says, get the symbols down. So what does that mean? Well, what we want to do is read through the sentence and find all of the symbols and write them down. So the symbols, those are going to be things like, of course, the element symbols or any symbols of compounds of elements. That includes pluses and any arrows, like the reaction arrows that we need to write down. Now, before we do that, look at the second step here. It says, do the subscripts and charge balancing. That's in the second step. So in this first step, we're not going to do any subscripts. It's really important. We just want to write the symbols down in the most simple way possible without any worry about subscripts, coefficients, or anything. So let's do that. We see the first thing that's written here is magnesium metal. How can we symbolize that? That's right, we can use the elemental symbol for magnesium, which is Mg. Then it goes on to say, is combined with. Now that's like saying and or plus. So let's use the plus symbol here. Then we see chlorine gas. Chlorine symbol is Cl. And then it goes on to say to form magnesium chloride. That's the reaction that we're talking about here. It's the is combined with chlorine gas to form magnesium chloride. So we're going to draw a reaction forward arrow, and we're going to show the product over here. That's what we're forming. That's the product of the reaction. And what are the symbols for magnesium chloride? Well, we're going to have magnesium and chlorine in that compound. So let's just write the symbols with Mg and Cl next to each other, not worrying about the subscripts or anything else for now. These are the symbols that we're working with, and we've written them down. So we've got magnesium metal is combined with chlorine to form the product magnesium chloride. Great, that's our first step. Let's go to the second step, which is we're going to do the subscripts. I like to call this step charge balancing because it's very frequently what we have to do here. Whenever we're dealing with ionic compounds, we have to adjust the subscripts, of course, to take into account the charges of the ions in the compound. So our first step is just to write the symbols down, and then our second step is we're going to now adjust the subscripts and do charge balancing. So let's start over here with our product, which is magnesium chloride, and let's do some charge balancing. So first off, do you remember what the charge is of magnesium when it ionizes? That's right, magnesium is in group 2 of the periodic table. It's an alkaline earth metal. So when it ionizes, it forms a +2 charge, a +2 cation. Now what about chloride? That's right, chloride is in group 7 of the periodic table. It's one of the nonmetals. Specifically, it's in group 7, which is called the halogens. And as you might remember, the halogens all have a -1 charge when they ionize. So if magnesium is +2 when it ionizes, and chloride is -1 when it ionizes, what's the formula of the compound that's neutral from these different species? That's right, we need to balance the +2 charge on magnesium with 2 negative charges. We can get that from 2 different chloride anions. So our formula will have magnesium and 2 chlorine atoms. So it should have a subscript 2 next to chlorine. Great, so now we have charge balanced and completed the subscripts on our products. Let's go over to the reactant side and see if we need to do any subscripts over there. So as we're looking at the reactant side, we have the element magnesium, and with elements, we always have to check and see if they are diatomic elements in their natural state and adjust their subscripts accordingly. Now, magnesium as an element is not one of the diatomic elements, so we're not going to have to put a subscript there next to it. It's fine as it is. It's just Mg. Now let's go over to the next element here. We have chlorine, and it says it's chlorine gas. So that's telling us it's the element chlorine, and as you might remember, chlorine is one of the diatomic elements. That means we need to fix its subscript by putting a 2 here because there are 2 atoms of chlorine in chlorine gas. So with that, we've now completed the step 2, which is we've completed the subscripts and charge balancing on both the reactant side and the product side. So let's check off step 2 and move on to step 3. In step 3, we're completing the phases. Now, what we have to do is look at each of these substances and try to figure out what phase it's in, whether it's a solid, a liquid, a gas, or dissolved in water. Now, the way we do this is we put together some different pieces of information, sort of clues that we have. We can look at things like the clues in the sentence. We can also look at the periodic table and some of the tips that I showed up above. Notice here it says magnesium metal. We know magnesium is a metal, and it's not mercury. Mercury is the only liquid metal. So that means magnesium is a solid under normal conditions. So let's just write a solid there next to magnesium in parentheses. Then let's go over to the other reactant here, which is chlorine, and it says chlorine gas. Chlorine is one of the gases that we have. It's a diatomic gas. So let's put a G there. And then let's go over to our products. We know the product here is a compound, so it's not one of our elements on the periodic table, right? It's a combination of elements. And that brings up an important point. How can you predict the phase or state of matter for a compound? Well, we're going to give you some information about how to do that. One of those pieces of information is right up here, the remembering points that I showed you earlier. So it shows here that all metals, those are elemental metals like magnesium, are solids. Then there's this point which says all ionic compounds are solids. So if we have an ionic compound like the one we're looking at below, we can assume it's a solid. Now, what if it wasn't an ionic compound? What if it was a molecular compound? How are you going to know what state of matter that is? Now, here below, we're not looking at a molecular compound. It's an ionic one. So let's just write down that that's a solid first. And then what I'm going to tell you about molecular compounds is there's so much variation in their phases and states of matter that most of the time we're just going to have to tell you what those are. So that's not something that you have to worry about. What I do want you to know, though, is that ionic compounds we're going to assume are solids. So let's write that here next to magnesium chloride. All right, so that's our step 3, right? We just completed the phase step. And now we're at the last step, step 4, which is we got to do the coefficients and the mass balancing. Now here's where I want to make just emphasize this again. If you try to do step 4 before step 2, or if you skip step 2 and just go to step 4, you're not going to be able to do step 4 properly. And you'll also have some problems with step 2 if you do it out of order by doing step 4 first. So it's very important, especially, that you always do this step 2 before you do step 4. You do not want to do these 2 steps out of order. Okay, so let's see if we can balance the coefficients here. First, let's look at the metals. Do we have a balance on the metals? We have 1 magnesium on the left, and we have 1 magnesium on the right. So the metals are balanced. The nonmetals, let's take a look at those. We have 2 chlorine atoms in the compound, and then chlorine is diatomic, so it has its 2 coefficient, and so we're good there. So it looks to me already like this one is balanced. So that means we're done here with step 4. We've completed the balancing. So those are our 4 steps, and if we do those 4 steps in that order, we will generally arrive at a pretty easy solution to most of these problems where we're writing equations. How about let's take a look at the next example. This next example reads, aluminum is combined with bromine to form aluminum bromide. So let's start here with our first step and write the symbols down. If you want to give this a shot yourself, go ahead and pause the video and work through step 1. So the basic symbols that we have to write down first, of course, is aluminum. That's Al. Now, it looks like aluminum in this case is being combined with the other reactant, which is bromine. So let's write the symbol down for bromine, which is Br. Now, if we continue reading this, it says to form aluminum bromide. So now we're talking about the product side of the reaction. So we should have an arrow going forward to our single product here, which has aluminum and bromine in the formula. So it has Al and Br. So that's step 1, getting the symbols down. If you got step 1 right, great job. Now let's do step 2. This is where we do subscripts and charge balancing. Now if you want to give this a shot yourself, this is a good chance to pause the video and see if you can get the subscripts right. You're going to have to do some charge balancing, and also don't forget to check for diatomic elements. When you unpause the video, we'll discuss. Okay, so I'm going to start over here on the product side with aluminum bromide and figure out the subscripts. Now, a good question here is some people ask, does it matter which side I start on when I'm doing these subscripts? And the answer to that question is no. It doesn't matter if you start on the reactant side on the left or on the product side, which is on the right. You can start on either side you prefer. So let's do aluminum bromide. First, let's figure out what aluminum's charge is. We know it is a fixed charge metal, so we can answer that question. It's a +3 charge. What about bromide? Bromide is another halogen, and it has a -1 charge. So how do we get a neutral compound when we have a +3 metal? That's right, we need -3 to balance that +3 out. And how do we get that with bromide? Well, that's right, we need 3 total bromide because each one is a -1 charge. That gives us 3 negative. So the formula for aluminum bromide is Al and Br with a subscript 3 next to the Br to indicate there are 3 of those. This is the neutral aluminum bromide. So that's the subscripts for the product side. Let's go do subscripts over on the reactant side. We have aluminum and bromine over here. Are any of these diatomic elements? Well, aluminum isn't. It's just a regular elemental metal, so it doesn't have any subscripts. And then bromine. Is bromine one of our diatomic elements? Yes. Bromine has a subscript 2 because it's diatomic in its natural state. So now we've completed step 2, which is subscripts and charge balancing. Let's go on to the phases, which is step 3. If you want to pause the video and try this yourself, go right ahead. When you unpause the video, we'll discuss. Let's start with the phases over here on the left with aluminum. Aluminum, as we know, is one of the metals. Because it's a metal, we know that it is a solid. As long as it's not mercury, metals are solids. What about bromine? Well, bromine's one of the interesting ones. If you look back up here, you'll see on my list of tips, you'll see that liquids that we need to remember about are bromine, mercury, and water. And of course, bromine is bromine. So bromine is a liquid. So let's write that it has an L next to it. Now let's go over to the product side and figure out what phase or state of matter aluminum bromide is in. Because aluminum bromide is an ionic compound, we can safely assume it's a solid. So let's put parentheses with an S in between to indicate as such. So there we have step 3 completed. Now we go on to step 4, which is coefficients/mass balancing. I like to call this the mass balancing step because we're adjusting the quantities of things on the left and the right. I like to contrast that with step 2, which is where we do charge balancing. We always want to do charge balancing before mass balancing. So anyway, let's go ahead and do the mass balancing. Now take a look at this and then pause the video and see if you can see a good place to start when you're balancing the coefficients here. When you unpause the video, we'll discuss. Okay, so one of the tips that I've shown you is make odd numbers even. So if you look at the left and the right, we can see a pretty obvious odd numbered atom here that we're going to have to balance. If you notice that, it's bromine with a 3 subscript, great job. Making that bromide an even number is going to make balancing a lot easier. So let's start there. What can we do to make that an even number where currently it's odd? That's right, we can put a 2 coefficient right in front of the entire compound aluminum bromide. That gives us 6 bromides on the right-hand side. And we can balance that with bromine on the left by putting a 3 coefficient right in front. Notice, however, when we made bromide an even number by putting a 2 coefficient in front of aluminum bromide, we also affected another element. That's right, we affected aluminum. And that's usually a really good thing to notice. When you fix one element, notice what other element it's going to affect, and then rebalance that element on the left. So here we have the 2 aluminum, but over here there was only 1. So we need to rebalance by putting a 2 right in front of aluminum. So now I always like to go back and just do a quick double check to make sure that we have the right number and type of all of the elements. We have 2 aluminum over here, and we have 2 aluminum here. We have a total of 6 bromine over here, and we have a total of 6 bromine here. So everything is balanced, and we've completed step 4. We've also completed this reaction. So great job. Let's go on to the next page and try a few more examples, and then we'll also learn some other types of reactions. Here we have another example of a combination reaction. I can tell it's a combination reaction because it's described that way when we read through it. It says white phosphorus, and it gives us the formula for white phosphorus, which is P sub 4. This combines with sulfur to make solid diphosphorus pentasulfide. So let's go through our 4 steps, and if you want to go ahead, pause the video, maybe run through a few of these steps, maybe all of them if you feel comfortable with it, and then we'll discuss after you unpause the video. So first step here is I want to write down the symbols only. So I'm going to write down phosphorus, that's with a letter P, and then it says combines with sulfur, so I'm going to do the plus sign and then the letter S for sulfur, and then we're moving over to the product side, so we're going to put an arrow, and then it says solid diphosphorus pentasulfide. Now you might have noticed as you were going through this example that all of the subscripts are pretty much given to us. We see white phosphorus as the subscript 4, so let's put the subscript 4 down there. And then we have sulfur. What about its subscript? Well, sulfur is a nonmetal. It's not one of our diatomic elements, so it doesn't have any subscripts. Let's leave that blank. And then let's go over to the product side. We have diphosphorus pentasulfide. So this is a molecular compound. We can tell that because, for one, it has 2 nonmetals in it, phosphorus and sulfur, so necessarily it's molecular. Also, the name has a bunch of Latin prefixes in it. And those Latin prefixes actually tell us what the subscripts are. So we don't have to do any charge balancing because this is a molecular compound. And I think some people get confused with that. Remember, ionic compounds have charges, molecular ones don't. So we don't have to do charge balancing with molecular compounds. We just write the subscripts. So what's the subscript next to phosphorus? That's right, the word di, the prefix di, means 2, so let's put a 2 there. And then what about for sulfur? Sulfur has penta before it, so that has the subscript 5 right next to sulfur. We've now completed step 2, which is subscripts and charge balancing. Now we go on to step 3, which is phases. Now the phases step might be a little confusing here because none of the phases for these nonmetals are indicated for you. If you actually want to know what the phases are, there's a periodic table I put on Canvas that shows color-coded wise all the phases for different elements, and you can use that whenever you want. For now, I'm just going to tell you what the phases are. Phosphorus is a solid, sulfur is a solid, and then it says the compound here, diphosphorus pentasulfide, says that's a solid. So these are all solids. That's step 3, which is phases. Now, if this were an exam, I would have given you that phase information for these nonmetals because there wouldn't be a way for you to predict it. So don't worry about that. So that's step 3. We've completed that. Let's go to step 4, which is coefficients and mass balancing. Go ahead and pause the video and see if you can figure out the balancing for this example. There are different ways you could start with this. One of the ways is noticing that at the beginning, phosphorus is already unbalanced. So we have 4 phosphorus over here and then 2 over there. So we can start off simply just by balancing phosphorus on this side. So we can put a 2 over here, and now phosphorus is balanced. But notice when I did that, I had a direct impact on the number of sulfur atoms. So before I put this 2 here, we had 5 sulfur atoms. Now with that 2 here, I have a total of 10 sulfur atoms. So I'm going to have to rebalance sulfur on the left to fix that to 10. So how do I do that? Well, that's right, I put a 10 here. I have a 10 in front of sulfur, and now sulfur and phosphorus are both balanced. I'm going to put the 1 in here, even though it's not necessary, but just to fill in that space there. I don't like empty spaces. So there we go. We have now done coefficients and mass balancing, and this reaction is complete. So if you got that one right, great job. Now what we're going to do next is learn the second type of chemical reaction, which is the decomposition reaction. So let's take a look at what a decomposition reaction is, how it works, and then do a few examples with balancing. Now, a decomposition reaction is pretty much the exact opposite of the reaction we just looked at. The reaction we just looked at, again, is called the combination, and decomposition is the reverse of that. In a decomposition reaction, we're taking a single substance and breaking it up into multiple substances. So we just saw a combination, we're putting them together. In this one, we're taking them apart. So symbolically, we could write this out as A, and then it's changing, so we use a forward arrow, and then over here our product side is going to have more than one thing. So our starting material here is one type of thing, and then our product is more than one type of thing. So we have A goes to B plus C. Now, just another quick note about decomposition reactions is they very frequently require some energy input to allow them to occur. So we often see something like heating below the arrow for this. So I'm just going to write that there as a little, usually we see this. So let's take a look here at the first example, which is a calcium carbonate. It says calcium carbonate is heated to decompose it into calcium oxide and carbon dioxide. So we see that word there, to decompose. Decompose is telling us that's a decomposition reaction. And if we sort of break this up, we see the reactant side has calcium carbonate. The product side has 2 different things. It has calcium oxide and carbon dioxide. So let's follow our steps here. Let's follow our 4 steps and see if we can write down the reaction and then go through all of the steps and get something complete and balanced out at the end. Feel free to pause the video and try this out yourself. When you unpause the video, we'll discuss. So first step is let's write down these symbols. The first thing we see here is calcium carbonate. So we need to know the symbol for calcium and we need to know the symbol for carbonate. Calcium is Ca, and then if you know your polyatomic ions or if you have your list, you can look up carbonate. You'll find that carbonate has the formula CO with a subscript 3 next to the oxygen. So here we have the symbols for calcium and carbonate. We're going to figure out the subscripts in the second step. Now we see the words is heated to decompose it and then the products. So let's draw our forward arrow and then put the little triangle under the arrow for heating. Now we have to draw the symbols for our products. We have calcium oxide and carbon dioxide. Calcium oxide has calcium and oxygen in the formula. Carbon dioxide, a molecular compound, has carbon and oxygen in it as well. We've now completed step 1, which is writing down our symbols. Now we move on to step 2, which is subscripts and charge balancing. Let's start on the product side. First, with carbon dioxide. We know that the formula for carbon dioxide is CO2, and that's specified here in the name for that product. So we have C and then O and then a subscript 2. Let's now look at the other product, which is calcium oxide. Calcium is a group 2 metal, so it has a +2 charge. Oxide is in group 6 and has a -2 charge. So how do we balance these out? Well, that's right. They're already balanced if we have one of each. So we don't need to change the subscripts on calcium or oxygen in this formula. It's good as it is. Now let's go over to the reactant side. Here we have calcium and carbonate. And hopefully you know your carbonate charge. Its formula, of course, is CO subscript 3 with the oxygen. And as a whole unit, it has a -2 charge. So carbonate is -2 and calcium is +2. So we don't need any more carbonate to balance out the calcium. So the formula, calcium carbonate, as it's written, is correct. So now we've completed step 2, which is subscripts/charge balancing. Now let's go on to step 3, which is phases. So for any ionic compound here, we have to put in a solid. So calcium carbonate, is that ionic? Yes, so that's a solid. What about calcium oxide? Yes, that's also ionic, right? Calcium is a metal, oxygen is a nonmetal. So here's a solid again. What about carbon dioxide? That's right, carbon dioxide is in fact a gas, so we can put parentheses and the symbol G right next to carbon dioxide. Now we've completed step 3. Let's go on to step 4, where we're going to do coefficients and mass balancing. So go ahead and pause the video, look at the left-hand side, look at the right-hand side, and make sure all of the elements are balanced by adjusting coefficients. When you unpause the video, we'll go through it together. So first, let's start with calcium. That's our metal. So that's often a good place to look first. We see there's one metal on the left, one of the calcium metals, I should say, and there's a 1 on the right. So calcium is already balanced. Then let's check out carbon. We have 1 carbon over here on the left, 1 on the right, so that looks good. And then we see 3 oxygen atoms in calcium carbonate, so there's 3 over there. And here we have over here a separated version of oxygen. So we have 1 oxygen atom here and then oxygen over here with 2 subscripts, so that's a total of 3. So oxygen is in fact balanced as well as all the other elements if we just have the coefficients 1, 1, and 1 right here. So that's step 4, coefficients and mass balancing, and we're done with this example. Let's take a look at the next one. Here we see potassium chlorate is decomposed to potassium chloride and elemental oxygen. Let's turn this into a chemical equation by following our 4 steps. First, let's start by writing down the symbols. On the reactant side here, we have potassium chlorate. Potassium has the symbol K, and chlorate, what is that? Is that a chlorine atom? No, chlorate is not chloride. It's a different word and it has a different meaning. Chlorate is a polyatomic ion. Now, if you don't know what chlorate is, you're going to have to look it up on your polyatomic ion list. So go find your polyatomic ion list and then find the formula for chlorate and then write it down. Now, one of the really nice things about having that list of polyatomic ions memorized is you don't have to go and look them up all the time. Saves yourself a lot of time and a lot of work. So anyway, what is chlorate? Chlorate is Cl with oxygen in it, and it has a subscript 3 next to the oxygen. It has a -1 charge as well, but we'll worry about that later. So here we have the symbols for potassium and chlorate. Now we're going forward arrow because we're going to the decomposition to the product side. And on the product side, we have potassium and chloride, so K and Cl, and oxygen, so the symbol O. Now let's go do step 2, which is subscripts and charge balancing. I'm going to start on the product side like I usually do and work my way backwards. And the first thing we run into over here is elemental oxygen, or as the symbol O. Elemental oxygen is one of our diatomic elements, so it has the subscript 2. Then we go over to the other product, which is potassium chloride. Potassium chloride is an ionic compound, so we need to make sure it's charge balanced. Potassium has a +1 charge, chloride has a -1 charge, so the formula for potassium chloride is just KCl, so that's good. Then we go over to the reactant side. Here we have potassium chlorate. Potassium is a +1 charge, chlorate is a -1 charge, So here the formula is already balanced. We don't need to adjust any of the subscripts. So that's step 2, the subscripts charge balancing. Now we go on to step 3, which is phases. Our ionic compounds will be solids, so we have potassium chlorate, that's ionic and a solid. Potassium chloride, that's also ionic, so that's a solid. Oxygen is a gas, so that's G. And that's step 3, phases. And now we get to step 4, which is balancing by mass or coefficients. So I want you to go ahead and pause the video and spend a few moments making sure you can balance this equation. If you have a hard time finding a place to start, I'll give you a quick hint. Make odd even. After you unpause the video, we'll discuss. When I gave the hint make odd even, that refers specifically to this chlorate ion over here. Notice there are 3 oxygen atoms in that formula, but over here we have an even number because of oxygen gas being diatomic. We can fix this problem by making the odd-numbered oxygen atom on the left an even number. So if we put a 2, for example, as the coefficient in front of potassium chlorate, we now have 6 oxygen atoms on the left-hand side. And we can balance that with oxygen on the right by putting a 3 coefficient over here. Now we just have to look at balancing the rest of the elements. Notice when I put the 2 coefficient in front of potassium, that means we have 2 potassium atoms and 2 chlorine atoms as well. So I have to rebalance that on the right-hand side by putting a 2 coefficient right over here. Notice if you go and total up all of the different atoms, we have a balanced equation at this point. So now we've finished step 4, and this reaction is done. So far, we've learned about combination reactions and decomposition reactions, and now let's learn about a third category of chemical reactions. These are called combustion reactions. The interesting thing about combustion reactions is they're actually a lot like combination reactions. In fact, they're exactly like combination reactions, except we're combining with a very specific element. One of the elements in a combination reaction has to be oxygen. So let's write this down. A combustion reaction is a combination reaction, except we're combining with specifically oxygen. So it looks like this. We have some element or compound A that we're combining with oxygen, and then we make a product of those two things. These products specifically we call oxides. If we wanted to go and define what an oxide is, an oxide specifically is one type of element combined with oxygen. So oxides are naturally formed by combustion reactions. Now, one of the most common types of combustion reactions that you will see is when we combust something known as a hydrocarbon. A hydrocarbon is a compound that contains carbon and hydrogen as the elements. These are also known as organic compounds. Now, when we combust a hydrocarbon, we form very predictable oxides. We form the oxide of carbon, which is called carbon dioxide, and we form the oxide of hydrogen, which is water. So when we combust hydrocarbons, we form as products just carbon dioxide and just water. Let's go ahead and do our 4-step process and see if we can write down this reaction and then balance it. If you want to try this yourself, go ahead and pause the video. When you unpause the video, I'll go through it with you. Let's start here with step 1, where we want to write down the symbols. First, let's identify our starting material, our reactant. That happens to be propane gas. So let's write down the symbols C3H8. Now notice here that I'm shortcutting step 2 because we're given the subscripts here in the starting material. Now as you get more comfortable doing this kind of thing, that's fine, of course. We know what we're doing, so we can just write these subscripts down. Now what does it mean for it to be combusted? That means that the other reactant, the other starting material, is oxygen. So on the reactant side, we have propane, which is C3H8, and we have oxygen. Now let's draw our forward arrow and the products of this reaction. We know in combustion reactions that we're forming oxides of our starting materials, so we should have an oxide of carbon and an oxide of hydrogen. So now we've completed step 1. Let's move on to step 2, which is the subscripts. Let's start over here with the oxides. We know we're forming the oxide of carbon, and it specifically is carbon dioxide. So let's put our subscript 2 there. And then we're also forming water, so it's H2O. Let's go over to the left-hand side. We already had our subscripts for propane because those are given to us in the beginning. So we have C3H8, and we're combining with oxygen, which we know is a diatomic element, so it should have subscript 2. Now we've completed step 2. Let's move on to phases, step 3. We see that propane is indicated as a gas, so let's put the symbol G there. We also know oxygen is a gas, and then we also know carbon dioxide is a gas, so let's put a G there, and we know water is a liquid. Now actually, it's interesting, when this reaction is run, it generates a lot of heat, so it turns out the water is actually vaporized when it forms. So we're okay writing an L there, that's fine. I just wanted you to know it's probably actually a G in reality. Anyway, that's our conclusion of step 3, so we're done with phases. Let's go on to step 4, which is coefficients and mass balancing. Balancing this equation is a little bit tricky, probably the first time you do it. So this is a good opportunity for you to pause the video and work through it. There are multiple ways you can go about doing it. When you unpause the video, I'll show you probably what I think is the easiest way to do it. So go ahead, pause the video, and then when you unpause, we'll discuss. Okay, so the first thing I'm going to do is duplicate this reaction because I'm going to do multiple things with the coefficients as I go through it. And it's a lot easier if I have a second version of the equation to show you with. Now, one way you can approach this problem is by starting with the make odd even trick. Notice there are an odd number of carbon atoms over here on the left. There are 3. So we can sort of make that even by putting a 2 coefficient in front of propane. Now there are 6 carbon atoms, and if we go back to the right-hand side, we can rebalance carbon just by putting a 6 right over here. Now carbon is balanced. But notice when I put that 2 coefficient in front of propane, there are 16 hydrogen atoms. Now there are definitely not 16 hydrogen atoms right now on the right-hand side. So how do we fix that? That's right, we have to rebalance hydrogen by putting an 8 coefficient right in front of water. So now hydrogen is balanced. What about the last element, oxygen? Let's add up all the oxygen atoms on the right-hand side and then fix that on the left. Notice I have 6 times 2 oxygen atoms from carbon dioxide, so that's 12. And then I have 8 times 1 oxygen atoms from water, so that's 8. So if we add the 8 to 12, we get a total of 20 oxygen atoms on the right-hand side. Let's go fix that on the left-hand side. If I put a 10 coefficient here in front of elemental oxygen, that gives me 20 on the left. That matches with the 20 on the right. Now take a look at this balanced equation. Do you notice anything else that we could do to maybe improve things? That's right, we could simplify this further by simply dividing everything by the number 2. So for example, if I divide by 2, that would mean I only need one of these propane molecules to react with 5 molecules of oxygen, which would turn into 3 molecules of carbon dioxide and 4 molecules of water. And when I do that, we now have the simplest form of the balanced chemical equation for this particular reaction. So if you got that one right, great job. Let's go to the next page and look at another example of combustion. So here we have another example of a combustion reaction. What I want you to do is pause the video and work through the 4 steps that we've been doing so far. See if you can get the balanced chemical equation. Okay, so let's go ahead and do step 1. First, we need to write down the symbols. So we see on the reactant side, we have magnesium nitride, so the elements magnesium and nitrogen as a compound. Then we see magnesium nitride is being combusted, so we should have a combination reaction here with oxygen as the second reactant. Next, we see that the products of this reaction are magnesium oxide and gaseous nitrogen dioxide. So the first thing we should do as far as symbols go is draw a forward reaction arrow. The first of our products is magnesium oxide. Of course, that contains magnesium and oxygen as a compound. The second product here is nitrogen dioxide. So of course, that contains nitrogen and oxygen. So that's step 1. We have all of the symbols written. Let's go ahead and do step 2, subscripts and charge balancing. We can start over here with nitrogen dioxide. We have the Latin prefix di there telling us there are 2 oxygen atoms. So let's put that 2 subscript in to nitrogen dioxide. Because magnesium oxide contains a metal and a nonmetal, we need to go ahead and do charge balancing for these 2 elements. Because magnesium is in group 2, it's +2, and oxide is in group 6, so it has a -2 charge. If we have one of each of these, we have a neutral compound. Now let's go over to the reactant side. We know that oxygen is a diatomic element, so let's put the subscript 2 next to that one. And now we get to magnesium nitride. That's another ionic compound, so we have to do charge balancing. Magnesium is +2 and nitride is -3. In order to have a charged balanced compound, we need 3 magnesium ions with +2 for each one. That gives us a total of 6 positive charges from the metal side of this compound. We're going to need to balance this 6 positive charge with a 6 negative charge from nitride. To do that, we need to have a total of 2 nitride anions, because each one has a 3 negative charge. So taking a look at our balance sheet, we need to have subscripts 3 for magnesium and 2 for nitrogen. So that takes care of step 2, the subscripts and charge balancing. Let's move on to step 3, phases. For phases, we have first magnesium nitride, that's ionic, so therefore a solid. After that, we have oxygen, which is a gas. Then we get over to magnesium oxide, another ionic compound and also a solid. And finally, we get over to the molecular compound nitrogen dioxide, which we're told is a gas. So let's put a G next to nitrogen dioxide. Now that takes care of step 3, phases. Let's move on now to the final step, 4, doing coefficients and mass balancing. To start off balancing, notice that magnesium is unbalanced and it's also an odd number over here on the left. So let's put a 2 coefficient here to make it even. Now, of course, we have to rebalance magnesium on the right-hand side, so let's put a coefficient 6 in front of magnesium oxide. Notice now that magnesium is balanced, and we can move on to the other elements. So, for example, let's take a look at nitrogen. We see 4 nitrogen atoms on the left-hand side, but there aren't 4 on the right. So let's fix nitrogen by putting a 4 coefficient in front of nitrogen dioxide. Now, the only thing we have left to worry about is oxygen. Let's add up all of the oxygen atoms on the right-hand side. We have 6 from magnesium oxide, and we have 8 from nitrogen dioxide. That gives us a grand total on the right-hand side of 14 oxygen atoms. Now let's go fix oxygen on the left-hand side. What coefficient do we need to put in front of diatomic oxygen to make 14? That's right, we need a 7 there. Now let's just double check and see if we can simplify this any further. It doesn't look like that because we can't evenly divide by 2. So at this point, we're balanced and we're done with step 4. So great job if you got that one right. And that brings us to the end of this lesson. In the next lesson, we're going to be learning about another type of chemical reaction, and that is specifically the single displacement reaction. Until then, I hope you're doing well. Please let me know if you have any questions, and I will see you soon. Take care.